Hi, welcome to a video on some graphical first and second derivative tests. So let's just say that we are given the graph of f prime of x, and we are asked to answer the following questions about the original function. So it is very important that you know that the graph that we are given right here is the derivative function. So what I'm going to go ahead and do is translate this into our first derivative number line test right below the graph. So I've drawn a number line, labeled it f prime of x, and from what we can see on this graph, f prime of x is 0 at x equals 0 and at x equals 4. So I'm going to go ahead and label those on my first derivative number line test. Now instead of me finding where the first derivative is 0 algebraically, I just looked graphically. The first derivative function crosses the x-axis, or is 0, at x equals 0 and x equals 4. And then what I also notice is that to the left of 0, so let's say x equals -1, x equals -2, x equals -3, etc., all of my first derivative values there are positive, which means if I put in -2 into the first derivative, I get a positive value out. Okay, so I label on my first derivative number line test a positive, which means my original function there is increasing, and I will draw an arrow showing. Then in between x equals 0 and x equals 4, I notice that, for example, at an x value of 2, my first derivative is negative, which means that the original function would have been decreasing, or something like so. I draw an arrow accordingly. And then after x equals 4, maybe x equals 5 or 6, I will notice that my first derivative has a positive output, which means my original function was increasing, and I will draw it accordingly. So remember, a first derivative function is used to describe the original curve. So I can answer those questions. But what I would like to do is further do a second derivative test given this first derivative graph. So I'm going to draw a second derivative number line test. And now what we're looking for is a second derivative, if you think about it, is really a derivative of a derivative. So in other words, my second derivative, let's see if I can put this over here in words, is going to be the same thing as the slope of the tangent line of the first derivative. Because again, we're saying that it's the derivative of the derivative, and a derivative is really just a slope of a tangent line. So now I'm describing and looking at this curve that I was given. It's the derivative function. So I'm looking at the slopes of the tangent lines. So now what I can say is the slope of the tangent line appears to be 0 when x is 2. So in between, let's see, 0 and 4, I'll put x equals 2 about right here, because I do want my first derivative number line test and my second derivative number line test to line up. And that seems to be the only turning point, or the only place where my second derivative would be 0. And then if we look, all of the values to the left of that, so all of these x values here, are going to have the same behavior in terms of the slope of the tangent line of that function. And all of those are negative, which means, because it's on a second derivative number line test, that my function is concave down in that interval. And then after x equals 2, so on this side of that graph, if I'm describing all of the slopes of the tangent lines of that curve, I would say that they're definitely all positive, right, because it's increasing. And so that means that my second derivative conclusion would be concave up. Okay, so now I believe I can go back and answer all of the questions that we were asked about the function. So where is my function increasing? Well, it is increasing from -infinity to 0 and 4 to infinity. Right? That's where my original function is increasing. So it's decreasing then in between 0 and 4. And what are the x values for the relative maximum and or relative minimum? Well, in this example here, we're going to increase to our maximum and turn around and decrease after. So I would say my relative maximum is at x equals 0. And I would say then my relative minimum, I decrease to a min and increase after. So that would be at x equals 4. I can also tell by the concavity because in that interval at x equals 4, I am concave up and I know I have a relative maximum or minimum there. So I am concave down. We said now we're looking at the second derivative number line test for concavity. And we read this number line to be from negative infinity to infinity, stopping at 2. And so I'm concave down from negative infinity to 2 and up from 2 to infinity. So my only inflection point would be at x equals 2. Okay, let's take a look at another one. Okay, here again we're given a first derivative functions graph, and there's a little bit more complex things going on here. What I can see is that we're still looking negative infinity to infinity for x, and there's no points of discontinuity, or so it appears from what I'm looking at. So I'm just going to go ahead and make a first derivative number line test corresponding to the graph that I'm seeing. And then from that, we'll go ahead and make our second derivative number line test as well. First derivative number line test, since we're looking at the first derivative function, I'm first just looking for where is f prime of x equal to 0. So I'm labeling all of those for us right now. And so it appears to be at negative 1, 0, x equals 2, and x equals 3. And from what I can see from this graph, my first derivative values are positive when I'm above the x-axis. So in that interval, this interval, this interval, and finally this interval. Okay, so everything I've highlighted in yellow is above the x-axis. So that would be where my first derivative is positive. And then here's an interval where my first derivative is below the x-axis or negative. So I'll label that on my number line accordingly. I am positive or above the x-axis, all except for between 2 and 3. In between x equals 2 and x equals 3, I am below the x-axis, which means my first derivative values are negative there. So again, a first derivative that is positive means your original function is increasing. So it appears that I'm increasing quite a bit. And then in between 2 and 3, we see that our first derivative is negative, which means my original function is decreasing there. And now we'll go to our second derivative test, which should sort of verify some of these things that we're seeing. Okay, I'm going to make a number line here for the second derivative number line test. Same thing, I'm sort of heading negative infinity to infinity, so if that helps you label that on your number line, go ahead. And for a second derivative, remember that is a derivative of a derivative. So it is the slope of a tangent line of our derivative function. So the slope of my tangent line is 0 right here at negative 1, maybe somewhere in between negative 1 and 0, so maybe negative 1/2. And it looks like 0. And it looks like maybe 1.5. Again, you're reading a graph, so whatever you think this x value is, it looks about like 1.5. And maybe 2.5 if I think about this horizontal tangent line down there. And that appears to be it. So I have negative 1, I have negative half, we had 0, 1.5, and 2.5. And I try to line these up with my first derivative test best I can because, for example, if you were on a continuous function, you are not both a relative max or min, so at a turning point, and a change in concavity or a point of inflection at the same time. So I'll say that again. You can't be a relative maximum or minimum and a point of inflection on the curve at the same time. Sometimes you'll notice points of discontinuity being used more than once because you may change concavity. So now what I'm looking for is I'm trying to describe the slopes of the tangent lines. So I am decreasing from negative infinity to negative 1, which means the slopes of all of those tangent lines that I just highlighted green are going to be negative. So from negative infinity to negative 1, my second derivative is negative, which means my original function was concave down. I'm going to run out of space, so I'm just going to write C for concave right now. And then in between, if I erase this so I can really truly see here, in between negative 1 and negative 0.5, I am increasing or having positive sloping tangent lines of the first derivative graph, which means my second derivative is positive. So therefore, I'm concave up. So I do have a change in concavity at negative 1. Now from negative half to 0 in this next section, I can see, and I'm exaggerating it a little bit, but I have negative sloping tangent lines, which means my original function would be concave down, because negative second derivative means concave down. So I do change concavity at negative half, so I'll circle that. And then in between 0 and 1.5, I am increasing again. So those would be positive, concave up for my function. So I went from down to up, so 0 is going to be a point of inflection. And then at 1.5 to 2.5, I am decreasing on my first derivative graph, which means my second derivative is negative. So my original function would be concave down. So again, 1.5 is a point of inflection. And then after 2.5, after x equals 2.5, I can see that all the slopes of the tangent lines here will be positive, which means my second derivative is positive. My original function will be concave up in that interval, so 2.5 is also a point of inflection. So now I'm going to read the number lines and fill in the answers. So where is the original function increasing? Well, it's increasing for all of these intervals. And technically, at the point where your first derivative is 0, you're not actually increasing. So we are going to use parentheses for these. So we'll say negative infinity to negative 1, and then negative 1 to 0, and then 0 to 2, and then 3 to infinity. So it's only decreasing in between 2 and 3. Those are x values, of course. So where is a relative maximum? Well, a relative maximum, I'm going to increase to a maximum, turn around and decrease. So that's at x equals 2. Relative minimum, I can see that I decrease to a min at x equals 3 and turn around and increase. So at x equals 3. Concave down, well, so I have a few intervals here, negative infinity to negative 1, negative a half to 0, and 1.5 to 2.5. And concave up the others, so negative 1 to negative 1/2, and 0 to 1.5, and 2.5 to infinity. Now, if you look, you should be going negative infinity to infinity. For example, concave down starts negative infinity to negative 1. Then you pick back up negative 1 to negative half, negative half to 0, 0 to 1.5, 1.5 to 2.5, and then 2.5 to infinity. So I do have from negative infinity to infinity. I haven't skipped any intervals. And what are the x values of the points of inflection? Well, there's quite a few. So I'll just list them at x equals negative 1, negative a half, because any change in concavity leads to that point of inflection there. That's a point on the curve. X equals 0, 1.5, and 2.5. And I believe I've got them all. Negative 1, negative half, 0, 1.5, 2.5. Perfect. So I hope you found this video helpful getting us started, and think about what would happen if there are points of discontinuity on your f prime of x graph, and we will dive into that on a later video. Thanks for watching.